Hello, I'm Jinbi M from Naver Cloud. I'll present our work, EGTR, extracting graph from transformer for scene graph generation. Scene graph generation aims to predict scene graphs with objects as nodes and relations as edges. Most previous studies took two-stage GG approaches that detect objects and then predict their relations. Recently, one-stage GG approaches that perform object detection and relation prediction at once have been studied, leveraging one-stage object detectors such as DTR. We categorize the existing one-stage SGG models into three distinct groups. Since edges in a scene graph can be represented as subject-predicate-object triplets, many studies embraced triplet-based approaches. However, object triplet detection models required sophisticated triplet detectors to obtain the necessary information for triplet queries from the object detector. Moreover, triplet detection models lack the ability to detect objects without relation by focusing solely on triplet detection without an object's detector. Relation extraction models that extract a scene graph without separate triplet queries or detection models did not use inherent relationship information among the object's queries in the object's detector other than the final hidden representations. We hypothesize that self-attention between object queries learned in a one-stage object detector might contain valuable information for predicting triplet outputs. In our preliminary investigation, we can extract a plausible attention graph by simply connecting two object queries with high attention weights from the pre-trained DTR. We propose a lightweight one-stage scene graph generator, EGTR, which stands for extracting graph from transformer. EGTR consists of DTR and a lightweight relation head, and utilizes relation information between object queries learned from the self-attention of the DTR decoder. We regard the attention queries and keys as subjects and objects, respectively, and obtain relation representations from them. Instead of using the self-attention weights as is, we concatenate the representations on all pairs of attention queries and keys to preserve rich information learned in the self-attention layers. Furthermore, we introduce a gating mechanism to use the various information learned in all layers effectively. We extract the relation graph from the gated summation of the relation representations across all layers. Since the number of object queries n is set to large enough to cover objects in the image, the ground truth relation graph G is severely sparse. From the bipartite matching results between object queries and ground truth objects, we divide G into three regions and apply different techniques for each region. We propose a novel adaptive smoothing for the GT region. We measure the uncertainty of each object candidate with the corresponding bipartite matching cost and smooth relation labels from the uncertainties of each object pair. With adaptive smoothing, the model is trained with a continuous curriculum that initially focuses on object detection and gradually performs multitask learning. We introduce hard negative mining to diminish sparsity for the negative and non-matching regions. Furthermore, we propose a connectivity prediction that predicts whether at least one edge between two object nodes exists as an auxiliary task of the relation extraction. In experiments on the visual genome dataset, EGTR showed the highest object detection performance and comparable triplet detection performance with the smallest number of parameters and the fastest inference speed. The experiments conducted on the OpenImage v6 dataset also demonstrate competitive performance, underscoring the effectiveness and robustness of our method across different datasets. For the ablation study on relation source, we verified the benefits of using attention queries and keys compared to the hidden states of each layer. As a relation source, attention byproducts showed similar triplet detection performance to the final hidden states, and incorporating both yields improved performance. The ablation study on proposed techniques demonstrates that our proposed techniques help to train the model framework effectively. We compare our method with two triplet detection-based models regarding the highest object detection performance. We show quantitatively and qualitatively that EGTR can better detect objects without relations than the triplet detection-based models. To sum up, We propose EGTR that generates scene graphs efficiently and effectively by utilizing the multi-head self-attention by products from the object detector. We propose several training techniques, such as adaptive smoothing and connectivity prediction. With the highest efficiency, our method achieves the highest object detection performance and comparable triplet detection performance. Thank you for watching our video.